Hello children, welcome back to the channel. Today we will be continuing our discussion of Newton's laws of gravitation and try to find the vector formulation for the law. See, we already have known discussed in our previous video that force of attraction between any two given masses in the universe is given by this expression, right? F is equal to G, where G is the universal gravitational constant, m1 m2 by r square, where r is the distance between the two. Now we said that this is a force and this is a force of attraction. Also what we have said is that since it is a force, so it must be a vector, and so we want to find a vector expression for this force. So let us consider two masses m1 and m2 separated by a distance of r. Okay, then what we will have is that m1 will be attracted towards m2 by a force, right, which will be given by force on 1 due to 2. This is a vector. Similarly, m2 will also be attracted towards m1 by the same amount of same force of same magnitude f on 2 due to 1. However, since these are vectors, so their directions do matter, right? Now, what is the direction of the force on 1 due to 2? To find this, first we need to find what is the direction of m1 with respect to m2. So, what we can say is that, see from this diagram, is that from m1 to m2, this r, if I skip from m1 to m2, with respect to m1, the position of m2 will be given by r12 vector, and its direction will be from m1 to m2. Whereas the position of m1 with respect to m2 will be given by the vector r21, whose direction will have to be from m2 to m1. Okay, so if we consider the direction, then the direction of vector r21 will be given by r21, a unit vector in the direction of r21, and the direction of r12, that is position of m2 with respect to m1, will be given by r12 cap. That is the unit vector in the direction of the vector r21, the position vector of r12, that is the position vector of m2 with respect to m1. Clear? Now, if we go to Newton's law, it says that the force of attraction between the two will be G m1 m2 by r. Now, if I consider the force exerted on 1 due to 2, this vector, then what we will get is that force is exerted by 2 on 1, so it will have to be taken in the direction of r21. However, you can clearly see that r21 is from 2 to 1, whereas force on 1 due to 2 is from 1 to 2, particle number 1 to particle number 2. So, the direction of the force is opposite to the unit vector's direction. So, we will get a negative here because r21 is equal to minus the unit vector in the opposite direction of r21 will be minus r21. So we have taken the negative sign here. Similarly, if we consider force of particle 2 due to 1, we still get G m1 m2 by r squared. The magnitude will remain same. This time we will take the unit vector from 1 to 2 because it is the force exerted by 1 on 2. Again, force exerted on 2 or by 1, that is, will be in the direction opposite to the unit vector r12, so it will be minus of this. Okay, now we already know that minus vector r12, the direction, r12's direction and r21's direction are basically opposite. So if I take minus r12 vector, unit vector r12, then we get r21. right? So we can rewrite this equation as G m1 m2 by r square r21 vector. Now if we consider this expression, the first one, force on 1 due to 2, and this expression that we have found here, this part, all the things are same, only difference is that this one has a negative sign. So we can clearly see that this value is equal to minus of F12, force on 1 due to 2. That is to say, force on particle 2 due to 1 equal to minus of force on particle 1 due to 2. Right? Which means these two forces, F12 and F21, create an action and reaction pair. And so, since these two are action and reaction pair, internal forces acting on two different objects having same equal magnitude but opposite directions, so they will surely have to follow Newton's third law of motion. Okay. Next important point is that r12 vector and r21 vector are opposite to each other, which means that they are acting along the same line joining the two centers of the objects. So, since both the forces F12 and F21 both have the same line of action, and from the center to center, right? So, this is a central force. It depends only on the distance between the two masses. There is no other type of dependency in terms of angular dependence or anything else. These two forces of gravitation, on one due to other and the second due to the first, depend only on the distance between the two and always act along the line joining them, so it's a central force. Also, we already have seen that not only it depends on the distance between the two objects, it also, what we have seen is that it follows 1 by r square. It varies as 1 by r square. We discussed it in the previous video also. If you haven't seen that, you may please refer to my previous video. The link will be given in the description along with my other playlist on other topics of class 11. So, since it follows inverse square law, if a force varies as square of the distance, inversely as square of the distance, we say that it is following inverse square law of distance. And so, as we have discussed in our earlier chapter where we discussed about conservative forces, we say that if a force is central and follows inverse square law, then it will be a conservative force. So, gravitational force of gravitation is a conservative force, which means, by definition, work done in a gravitational field or moving an object from one point to another in a gravitational field, which we will discuss in a little while, in a couple of videos time, is independent of the path taken. Or, in a gravitational field, if an object starts from one point and moves about and then comes back to the same point, total work done will be 0. Okay. And one last thing, while we are talking about the properties of gravitation or force of gravitation, is that if we have two masses, the force of gravitation depends on the magnitude of the masses, that is their product, and the distance between them, that is it varies inversely as the square of the distance. It doesn't care about the intervening medium between the two masses. That is to say, if we have taken two masses and found the gravitational force between them on Earth's surface where there is air between the two masses, right? So it air being a medium, there is an intervening medium here. Or we take the same two masses and put it under water and take the gravitational force between them. Or we take the two masses and go to the space which is vacuum and take the gravitational force between them. All the cases, as long as the distances are the same and the masses are the same, the force of gravitation will be the same. So gravitational force F gravitational is independent of the intervening medium. And since it is independent of the intervening medium, that is why this constant of proportionality G is a universal constant. It will be a constant everywhere in the universe, whether there is a medium between the two masses or not. The constant of proportionality will remain the same. So we have discussed about the vector form and the various properties of force of gravitation. Now let us consider we have a mass at some point, given point P, say, and there is a distribution of mass around it, say m1, there is m2, m3, and so on, n number of masses. Okay, and each of the masses will exert force on this particular given mass. Due to m1, it will be, say, if the mass of this particular point mass P is m, then for m1 it will be g m1 into m divided by the distance between these two, say r1, and so on and so forth. So let's call this force of attraction due to m1 on P be F1. Force of attraction on m1 due to m2, so this mass due to m2 will be F2. Force of attraction on P, or this point mass m, due to m3 will be F3, and so on and so forth. All are vectors, please note that. So they will be acting along the line joining them, and the force will be towards, it will be pulling the mass towards m1, right? Or it will be pulling the same mass, m2 will pull it towards itself, that's m2, towards m3, and so on. So there is a principle of superposition which says that the gravitational force of attraction between any two given mass, let's consider this mass and m1, then the gravitational force of attraction between these two masses is independent of presence or absence of any other masses. What it means is that whether this m3, m2 and the other masses were there or not, the force of gravitational attraction between these two masses will remain constant or the same. If the masses are there, they are not going to hamper the force of attraction between these two. Similarly, for the mass m2, for mass m3, for all the different masses, the force of gravitational attraction between the given mass and that mass will not be altered due to the presence of other masses or due to the absence of other masses. Which means this F1 will be the same as long as the distance is the same. Okay. So what it means is that the net force on this point P, if I call this the resultant force Fr, due to this mass distribution around it, m1, m2, m3 till mn, will simply be the sum of the gravitational forces of attraction between each pair, that is this mass and m1, this mass and m3, this mass and m2, this mass and mn, and so on and so forth. Which means that it will be just the vector sum of f1 plus f2 plus f3 till the nth particle. Or we can simply say this is the summation I equal to 1 to n fi. Okay. So principle of superposition simply says that gravitational force of attraction between two particles is independent of presence of other particles, and if we have to find the net gravitational force of attraction on a single particle, then we simply take the vector sum of all the gravitational forces of attraction due to all the particles around it. Alright, now for the shell theorem or Newton's shell theorem. So what it says that the shell theorem gives us a measure of gravitational force of attraction on a point due to a spherical shell, that is, the inside of it is hollow and the mass is distributed on the shell itself, or a uniform spherical mass distribution. This is a solid sphere and the mass distribution in it is uniform. So the shell theorem gives us the gravitational force of attraction due to these two. Let's first start with a point outside the distribution. Let's say this is the radius of the shell or this is the radius of the solid sphere. Okay, and let's say we have a point P outside at a distance of, say, r. For both the cases it will be similar, so we will have the similar point and the similar distance r. Okay, in that case what we will have is that for outside point, when the point P is outside the shell or the solid sphere, the uniform mass distribution, the gravitational attraction will be as if the entire mass of the shell or the sphere was concentrated at the center of it, here or here. So what it means is that if this has a mass, some mass, say small m, and the shell has a mass of or capital M, or the sphere has a mass of capital M, and this point has a small mass of m or mass m, then the distribution, disregarding the distribution, mass distribution, the entire mass will act as if it was concentrated at the center, which means when we apply the formula F is equal to Gm capital M small m, the two masses, by r squared, this distance will be measured from the center of the shell or the center of the uniform solid sphere, uniform mass distribution, solid mass distribution. So this distance will be the r here. Okay, this is for r greater than or even equal to the radius of the sphere. So even if the object was at the surface of the spherical mass distribution or the solid sphere, uniform solid sphere, the force of attraction will be given by Gmm by r square, where r is the distance from the center to the point. Now for a point inside the shell or the solid sphere. So if we consider the shell first, let's say the particle is now at this point, this distance is r. In that case, Newton's shell theorem states that the force exerted on this by the entire solid shell or entire the spherical distribution, that is shell, will be F will be equal to 0. So net force acting on this gravitational attraction, force of attraction due to this distribution which is around the body now, will sum up to be equal to 0. We need to remember that. Now for the solid sphere, say again this is the distance r, and we can always draw a inner sphere of radius r around it, right? So for shell, spherical shell, F will be 0. For solid sphere, uniform solid sphere or uniform mass distribution, distributed solid in a uniformly distributed solid sphere. In this case, what will happen is that the force of gravitation will be acting, even if it is inside, the point is inside, the force of gravitation will be acting towards the center of the shell and towards the center of the sphere, and also the mass, the first mass, that is F equal to G m, small m is the mass of the particle here, the G m will be for the inner sphere of radius small r. That is to say, if we take the distance of the point mass inside the uniform solid sphere as the radius and draw a sphere having the same center, a concentric sphere inside the given solid sphere, then the mass of the inner sphere will be taken for the force of gravitation, and then we have of course r square, where r is this distance of the particle from the center. Now, what was the mass of the entire sphere? This would have been 4 by 3 pi r cube into density of the matter, and the mass of the inner sphere r for radius r will be 4 by 3 pi r cube into this, right, which gives us m r by n equals to only r cube by capital R cube, or we can say that m r will be r cube by capital R cube into capital M. If we substitute this value of mr in this equation, what we get? Let's see, g m by r square, and we substitute mr, right? R cube by r cube into m, right? Fine. So this will be g, capital M can come here, small m by r cube, and from these two we only have r. So force of gravitational attraction inside the solid sphere will simply be this. Okay. Now we have already seen that inside a spherical shell, where the mass is distributed on the surface of the sphere, inside it the force of gravitational attraction is 0. However, this is due to the shell only. If there are other masses outside it, say we have another mass here, we have another mass here, so different masses there, then these masses gravitational attraction on this given point inside the spherical shell will still be felt, which means that the spherical shell cannot shield the gravitational attraction of other particles in the vicinity or around the given particle. What it does is that due to the spherical symmetry of the mass distribution, the net force acting on this due to the shell only will sum up to be equal to 0. But this does not shield the given mass inside the shell from outside influence, that is for gravitational attraction of force particles lying outside the shell, which means that gravitational shielding is not possible. Right, so we can of course shield, we'll see in class 12 that we can shield a given charge from outside influence by putting it inside a metallic container due to certain reasons which we will discuss later. However, in case of gravitational field's influence or gravitational forces influence or the influence of other masses on a given mass cannot be eliminated by keeping it in certain kind of container or keeping it in some special condition. A gravitational field is all permeating or will move into all the nooks and corners of the universe and will influence each and every particle. However, since its magnitude is very small, so normally the effect of gravitational field is felt only for massive objects. For example, the Earth's gravitational field or Earth's gravitational attraction, because of Earth's gravitational attraction, we are glued to the surface of the Earth, or any object falls towards the Earth, or due to the Sun's gravitational attraction only, the Earth moves around the Sun. However, due to the plane's gravitational attraction, I am not pulled towards it. Even if I am pulled towards it, the force is so weak that it is not giving me any kind of influence on it. So what it means is that as I am standing right here, I am subjected to gravitational attraction of many objects. Only point is that I am subjected to the gravitational attraction of the sun, of the moon, of the pen, of the board, of probably the outer planets of the solar system, of a black hole lying millions of light years away. I am subjected to gravitational attraction of all these. However, since these objects, other objects are much farther, and these objects like the pen or the board are much less massive, so their influence is not strong enough to affect me. However, the influence is still there.